Good morning to all of you. I welcomes to all in our lecture series on solid state physics. In our today's lecture, we are going to discuss about vibration of one-dimensional monoatomic lattice. So, this is the one of the diagram at the state of equilibrium of monoatomic lattice, means each lattice side one atom will be present. Suppose this is the one dimensional lattice. Periodic lattice means here is the point, then with a equal distance that point is repeated along x axis and the distance is a, and each and every side have only one atom. Okay, so only for that it is said as monoatomic lattice. So when this monoatomic lattice is going to be vibrate, what type of physical phenomenon we are going to be observed, that we are going to be discuss. Or we can say that this vibration, this lattice vibration may be in lower frequency, may be in higher frequency. So for what condition, or whenever it is vibrates with lower frequency, then it is how this lattice are going to be behave inside the crystal, and when it will be vibrate with higher frequency, then how its behavior for the crystal, that we are going to be discuss. So first, whatever the situation is in our figure, it is written in this 3 to 4 lines. I am just reading, you just watch it. Consider one dimensional chain of atoms where each atom has mass m and is attached to the other atoms by massless springs. So here each atoms is attached with a spring having the mass of the spring is taken as 0, means massless spring, and each atom have the mass is m. Here we have been considered the one dimensional chain of atoms. Okay. Initially consider the equilibrium state of the atoms. So this state is the state of equilibrium. Okay, when these are situated at equally spaced site represented by n2 minus 1, n minus 1, n minus 2, n minus 1, n plus 1, n plus 2, like that. That means along x axis this state is called as the state of equilibrium. When it is situated like this, suppose this site is named as n, this site is named as n plus 1, n plus 2, and this one n minus 1, n minus 2, n minus 3, so on, and n plus 2, n plus 3, and so on. Only we have been represented each and every atom site by this name n. Okay, this is the so called, we can say, the coordinates of each and every atoms of this 1D chain of atoms. Here A be the interatomic spacing. So at the state of equilibrium, this distance is nothing but called as the interatomic spacing. Okay. Hence x coordinate of corresponding atoms, if this atom is named as n, this atom is named as n plus 1, n plus 2, like that. So the corresponding x coordinate of corresponding atoms will be, this will be Na. Okay, Na, the coordinate will be Na, and this coordinate will be n plus 1a. The coordinate of this atom will be n plus 2a. Coordinate of this atom will be n minus 1a. Coordinate of this will be n minus 2a, and like that. So here I suggest to you, first watch the video carefully, then you have to write the notes you have to pause the video and you can write the notes, no problem. So here let the lattice starts vibration. So this is the state of equilibrium, and we have to consider the state of displacement. Displacement means suppose this is the chain and I am going to be drag this one somewhat this side, and if I'm going to drag this one dimensional chain, and if I'm going to be drag and leave, so if I am going to drag this one and leave, or if I am going to give a force this side, then these atoms on this chain, they are going to be vibrate like this. One dimensionally they are going to be vibrate like this. Okay, all the atoms. So at a particular state, or we can say at a particular instant, or that is the so-called state of displacement, is represented by this one. That means this position will be the equilibrium position at the state of equilibrium. So at a particular instant of time, suppose this atom is displaced this distance, this atom has been displaced this much distance from its equilibrium position, and this atom has been displaced this much distance from its equilibrium position. Likewise, this atom equilibrium position will be here, and this atom is displaced this distance, that is represented by un minus 1. These are the subscript. Okay, un, n is subscript, u of n plus 1, n plus 1 is also in subscript. Okay, and un plus 2, this is n plus 2, n plus 2 also subscript. So here we consider that n plus 2, n plus 1, n minus 1, n minus 2 are the displacements at a particular instant when this one dimensional atomic chain or one dimensional lattice starts to vibrate. So here let the lattice starts vibration along x-axis. Okay, due to vibration the atom executes periodic motion about their equilibrium position and becomes source of elastic waves which propagates through the medium. So suppose you can think that suppose this is a electron. Okay, suppose this is a electron. If electron is going to vibrate with a particular frequency, then we can found the so-called EM wave will be propagated. Electromagnetic wave is going to be propagated. So by any cause, by any means or by any cause, if this lattice, one dimensional lattice is going to take energy from outside and starts vibrates, each lattice sides vibrates about their mean position. This will vibrate about their mean position, about its mean position. This will vibrate about its mean position. This will vibrate, and this will be vibrate about its mean position. When it will be vibrate, that vibration will be nothing but so-called the periodic motion. We can say that the with vibrates, or we can say the simple harmonic motion, or we can say the periodic motion about its mean position. Due to this vibration, a wave will be propagated. Due to this, from this atom, a wave will be propagated. From this atom, a wave will be propagated. This atom, a wave will be propagated. So we can say that at a particular instant, these are the displacements of each atoms of each sides. So for a, if we are going to consider n atom, nth atom, this is nth atom, the displacement is un. N plus 1th atom, the displacement is un plus 1. Suppose at an instant, these are the displacements of the lattice sides or the atoms situated at different lattice sides. Okay. So these are the things here it is written in the note. Let at any instant of time the displacements of n minus 2th, n minus 1th, nth, n plus 1, n plus 2th atoms from their mean position be un minus 2, un minus 1, un plus 1, un plus 2, like that respectively in the state of displacement, which is figure this one. This is the figure of this one, state of displacement from their equilibrium positions. Okay. So in this case, it is assumed that the spring are ideally elastic, hence the force between any two atoms will be linear. That is, the force required to produce an atomic displacement is proportional to the displacement itself. So here it has been assumed that the springs are ideal elastic in nature. That means how much we have to apply the force, or the force need to displace the atom towards one direction, it is proportional to the displacement. It is proportional to the displacement. So as the springs are considered as ideally elastic, hence the force between any two atoms will be linear. That is, the force required to produce an atomic displacement is proportional to the displacement itself. So what is the meaning of that elastic nature and it is linear and displacement is proportional to the displacement itself? That I am going to show you with an example. You just observe. So this is the initial situation that one spring is attached to a mass. Okay, you just see, I displaced this much and I lived. How much restoring force or how much it has been came back, you just observe. I displaced this much distance, I lived. In which force it has to come back? This is the first case, suppose, and I displaced more and I lived. And this object is going to be came back to its original position with higher force. That means if this spring will be a full elastic, so here whenever we are going to consider this spring is full elastic, then how much I have to displace this object towards the right side, that much amount of restoring force will be induced in this string which tries to pull the object towards its mean position. So only for that it is written that the force required to produce an atomic displacement is proportional to the displacement itself. That means how much I have to displace, that much force is required. So this much, suppose this is 1 centimeter, I have to be displaced. What will be the force is required? If I will be displaced 2 centimeter, again another 1 centimeter, then the force required more. Another 1 centimeter, then another, then the force we need will be more force. That means suppose this is our this is the origin and this is our the length. Okay, this is the situation. Suppose at initial the object or the atom will be at here. It is attached with a spring or the so-called elastic, full elastic. So suppose this distance are equal distance. Whenever I displace this atom from 1 to 2, suppose this is 1 to 2 is 1 centimeter, 1 centimeter and 1 centimeter. If whenever I have to displace this atom, how much induced restoring force in this string, if I will be displaced from 2 to 3, the restoring force will be increased. That means how much force I need to displace this atom from 1 to 2, from 2 to 3 I need more force to displace because the restoring force induced more. Hence it has been written over here that the force required to produce an atomic displacement is proportional to the displacement itself, because elastic nature of the spring, ideal elastic nature. Okay, so hence or here I have also written that, or in this way you can understand, we can say that the restoring force is also proportional to the displacement. How much we have to increase the displacement, the inducing of the restoring force inside the string also proportional to the displacement. Okay, here beta, let beta be the force constant of the spring and u be any arbitrary displacement. If we consider this one, that maybe beta be the, suppose beta be the force constant of the spring and u be any arbitrary displacement for this one dimensional lattice structure, then the force exerted by the spring on an atom is F proportional to u, F proportional to u, then the force exerted by the spring for the displacement u on the atom will be proportional to that displacement, or we can write F equal to beta u. Let this is equation number 2. Now we have to consider the nth atom, whatever we drawn in the figure, in the case of displacement state. So for the nth atom, if we are going to consider nth atom, this is nth atom. This atom is displaced how much distance? Un distance from its equilibrium position. So the nth atom is attached with n minus 1th and n plus 1th atom by 2 springs. So if we are going to consider this atom is attached with n minus 1th atom and n plus 1th atom with 2 springs. Okay. Now, so it experiences 2 opposite forces, each one of which proportional to the net displacement of the corresponding spring. So now whenever this whole one dimensional lattice is going to be displaced towards this atom is displaced, this nth atom is displaced having the displacement of un. At that time n plus 1th atom is displaced of a distance un plus 1. So if we are going to consider the net displacement between these 2 atoms, this is displaced, this atom is displaced from here to here, this atom is displaced from here to here. What will be the net displacement if I am going to consider this atom and this atom? The net displacement will be un plus 1 minus un. Okay, un plus 1 minus un will be the net displacement. If it is so, then the force exerted on this by this atom towards this will be how much? Will be F un plus 1 minus un. So here un plus 1 minus un will be the net displacement comparing with this atom and this atom. Okay, so hence force on this atom due to this towards this will be how much? F will be equal to beta into un plus 1 minus un. Okay, likewise the force exerted by this atom on this atom towards this side will be nothing but the net displacement between these two atoms. What will the net displacement? The displacement of this atom will be un, and displacement of this atom will be is the un minus 1. So net displacement is how much? Un minus 1. So the force due to this atom on this towards this side will be how much? Will be beta into un minus 1. So one force, this atom is exerted force on this towards this side, and this atom exerted force on this towards this side. So here the net displacement between this and this is larger. You can see this minus this is larger than this minus this. So hence this force will be larger than this one, because we know that the force is proportional to the displacement, so here net displacement between this atom and this atom will be larger as compared to this atom and this atom. That means un plus 1 minus un is greater than that of un minus 1. So hence the net force towards right on this atom, on nth atom, will be how much? Beta into un plus 1 minus un minus beta into un minus 1, or that implies F equal to beta into un plus 1 plus un minus 1 minus 2 un. Let this is equation number 2. Using Newton's second law, Newton's second law, m can be written as mass into acceleration or mass into d square x by dt square. Here displacement is nothing but un, so m d square un by dt square will be equal to this much. So here this is represents the acceleration of nth atom, only m, this one, not m. I written mistakenly, you have to correct it. Okay, you correct it. This represents only m, only d square un by dt square represents the acceleration of the nth atom. Okay, so let this is equation number 3. Now the solution of this equation number 3 in general, we can found that it will be un will be u0 exponent of I omega t minus k na. So if we are going to try to find out its solution, the general solution, that solution will be in the form of what? That is un will be equal to u0 exponent of I omega t minus k n a, k into n a. See, these are the same things. Here I written in the form of exponent of I omega t minus k n a, or you can write e to the power I whatever. Let this is equation number 4. The above equation number 4 represents the displacement of nth atom. Here omega is the angular frequency, k is the 2 pi by lambda, that is nothing but wave number or wave vector or propagation vector. Okay. Similarly un plus 1 or the displacement of n plus 1th atom will be, that is un plus 1 will be equal to u0 e to the power I omega t minus k instead of n. Here for nth atom will be n, for n plus 1th atom it will be k into n plus 1 into a. Likewise for n minus 1th atom the displacement will be un minus 1. Here n plus 1, n minus 1 are in subscript. Okay, un minus 1 will be equal to u0 e to the power I omega t minus k into n minus a into n minus 1 into a. Let these two equations are equation number 5. By considering equation number 4 and 5, in equation number 3 we obtained that that means it is telling that suppose we are going to consider un, that is u0 e to the I omega t. In equation number 3 is in the form of what? That is m d square un by dt square. Now we are going to consider the d square un by dt square. How much we are going to get? How much? Suppose this is the un. The double derivative with respect to t, we can found that it will be double derivative. It will be with respect to t. It will be I square omega square. That means minus omega square un. We can found minus omega square un. Okay. So using the equation number 4 and 5, in equation number 3 we can obtain this one. Here I omitted many steps. You can do it in your rough. I am going to do for yourself, for you. You just watch. Okay. Equation number 3. Equation number 3 was what? That is m d square un by dt square will be equal to how much? It will be beta into un plus 1 plus un minus 1 and minus 2un. It is very easy. You just we have to put the values. That's it. So here un is how much? This one. Okay, and its double derivative d square un by dt square will be equal to, you just watch here, how much it will be? It will be I square omega square u0 into exponent to the power I omega t minus kna. Okay, or it will be minus omega square u0 into e to the power I omega t minus kna. Now the left hand side of this equation, this is our equation number 3. So the left hand side of the equation number 3 will be how much? Will be minus m omega square into u0 into e to the power I omega t minus kna. Okay, is equal to beta into un plus 1. Un plus 1 is this one. The value of un plus 1 is u0 e to the power I omega t minus k into n plus 1 into a. So here I can write that u0, see, instead of un plus 1 I can write that is u0 into e to the power I omega t minus k into n plus 1 into a. Okay, plus un minus 1 will be u0 into e to the power I omega t minus k into n minus 1 into a. Okay, plus, sorry, minus 2 into un is how much? Un is u0 into e to the power I omega t minus kna. Okay, so this right hand side again can be written as beta. This will be u0 into e to the power I omega t minus kna into e to the power minus I ka. Okay, you just consider this term. u0 will be here. This is u to the power I omega t minus kna is one term, and another is minus ka e to the power I e to the minus I ka. Okay, likewise this can be written as plus u0 into e to the power I omega t minus kna into e to the power I ka. Okay, minus 2 into u0 into e to the power I omega t minus kna. Okay, this is our right hand side, this is our left hand side. So if we are going to divide this term, left hand side and right hand side, if I am going to divide this term left hand side, I am going to get how much? Minus m omega square. Okay, if I am going to divide this term left hand side here, so it will be only minus m omega square. Minus m omega square is equal to, first divide with this term. This term means this will be 1, and this will be 1, this will be 1, and this will be 1. So it will be beta into e to the power minus ika plus e to the power ika minus 2. Okay, so this much steps I have been omitted because these are the simple steps you can do in your rough. So I have been written over here that using equation number 4 and 5 in equation number 3 we can obtain this one. Okay, see e to the power minus ika, e to the power minus ika, e to the power ika minus 2. Okay, so this is nothing but beta of e to the power I ka by 2 minus e to the power minus I ka by 2 whole square, that is a minus b square. If we are going to do a minus b square, it will be a square, a square, a square. This a square means e to the power ika, e to the power ika, b square plus b square, e to the power minus ika, e to the power minus ika, and minus 2 into a into b, minus 2 into a into b. A into b means it will be e to the power minus ika into e to the power plus ika. So e to the power 0 equal to 1. So this can be written in this form of a minus b whole square. So same thing I have been written over here. Okay, but we know that sin x is nothing but e to the power ix minus e to the power minus ix, e to the power ix minus e to the power minus ix divided by 2i. Here I mistakenly not written 2i. So that implies sin square x, obviously it will be square and I square will be minus 1, so it will be 1 by 4 e to the power ix minus e to the power minus ix whole square. Okay, so here this is also in the form of e to the power like ix minus e to the power minus ix square. So this can be written as this much value can be easily written as sin square ka by 2. Okay, so so that implies from equation number 6, we consider from equation number 6 we can found minus m omega square will be equal to how much? This will be written as this much is nothing but will be sin square ka by 2. Okay, sorry, this much will be equal to sin square ka by 2 whole divided by 4 minus, sorry, and I am doing simple mistake because see, no, actually this value will be nothing but, see, this much value will be nothing but 4 minus 4 sin square x. So this much value will be equal to minus, it will be minus 4 sin square x. So if I am going to compare this and this, I am going to found that minus 4 sin square ka by 2, actually not this one, this value will be equal to minus 4 sin square ka by 2. Okay, if I am going to compare this and this and this, then it will be minus 4 sin square ka by 2. Now equation number 6 will be minus m omega square will be equal to, this will be minus 4 sin square ka by 2. So it will be minus 4, beta will be already is there, minus 4 beta sin square ka by 2. See, I am explaining once again, simple things it is e to the power ix minus e to the power minus ix by 2i. We know that sin x. So hence sin square x will be equal to minus 1 by 4 e to the power ix minus e to the power minus ix square. That implies this much. This will be how much? This will be minus 4. This will be equal to this much will be equal to minus 4 sin square x. So if I am going to compare this one and this one, so instead of x we have to write ka by 2, minus 4 sin square ka by 2, and here equation number 6 will be minus m omega square minus 4 beta sin square ka by 2. That implies omega square will be equal to plus or minus 4 beta root over of 4 beta by m sin ka by 2. Let this is equation number your 7. Okay, let C and rho denoted the longitudinal stiffness and mass per unit length, and here I left, and this is represents the stiffness and this is represents the mass per unit length of the line, whatever we considered, along which the atoms are situated. So here these are the this is the mass per unit length of the line respectively. Then C will be stiffness will be nothing but spring constant into your interatomic distance, and density or the so called mass per unit length will be m by a. Okay, m by a. So it can be noticed that a line of length a contains a massless spring and an atom of mass m. Therefore equation number 7 becomes equation number 7. So here we can put, instead of beta we can put c by a, instead of m, instead of beta we can put c by a, instead of m we can put rho by a. So it will be, this equation number 7 can be written as plus or minus 2 by a c by rho root over sin ka by 2, plus or minus 2 by a. This is the unit of velocity. This is the unit of velocity. So it will be velocity or we can say the so called one constant but dimension of velocity. Okay, it will be b represented by bs sin ka by 2. This is equation number 8. Here bs is considered as constant having dimension of velocity. You can consider stiffness by mass per unit length. Obviously it will come as the so called dimension of velocity will be a constant. If it will be a uniform line, then it will be, this vs will be constant. Okay, so since frequency omega should always be positive irrespective of the sign of k, because this is the wave vector, direction of wave vector, then that may be along positive x-axis, that may be along negative x-axis. Hence we have to take the magnitude on the right hand side of the equation number 7 and 8. So equation number 7, here if we are going to consider omega will be this one. This is, oh sorry, this is omega, not omega square. Okay, this is omega, because omega square will be this much, so omega will be this much, so omega will be this one. So this is the two forms of the so called frequency of the waves or the oscillations of the sides of one dimensional lattice. So this is the frequency in the form of beta by beta and m, and this is the frequency in the form of stiffness and mass per unit length, and this is the dimension of velocity. And here this, as omega should be always positive, then equation number 7 that backs this page, and this if we are going to consider, the right side of the equation number 7 and 8. The right side of the equation number 7 means this side of equation number 7 and this side of equation number 8 should have to be taken as magnitude form. So omega will be equal to 4 beta by m root over magnitude of sine ka by 2, or it will be 2 by a vs. This is for this equation number 8, from the equation number 8, 2 by a vs sine ka by 2 modulus. This is equation number, this is equation number your 9. Okay. So this is 2 by a vs sine ka by 2 mod, and the solutions of the type, that is equation number 4 and 5, will be acceptable if omega is related to k as in equation number 9. So from the equation number 9 it can be straightforward, it can be found that k and omega is related directly. So here, as omega and k are directly related with each other, from this equation number 9 it has been found, then it is this equation will be called as the dispersion relation. So dispersion relation means whenever wave vector is related, the equation represents relation between wave vector and frequency. The wave vector and frequency related by any equation, if we are going to found in our future, then that will be called as dispersion relation. So this is belongs to the frequency of each and every sides is going to be oscillates. This sides is going to be oscillate with the frequency, that frequency, and the direction of the propagation of the waves due to the simple harmonic motion or periodic motion. From that side a wave will be propagated along a particular direction. That direction is represented by wave vector, that is k, but that k and omega is related by this equation number 9, and this equation number 9 will be called as dispersion relation. And this dispersion relation has been plotted over here, and about this graph, and from the dispersion relation we are going to find out many results that we are going to discuss in our next class. So at low frequency, what will be the physical dynamics, or what will be the relation of omega and k, and at higher frequency how the lattice vibration is going to behave, and which type of dynamics we are going to be get at the higher frequency and lower frequency, and other things we are going to be discussed. And this graph, related this graph also, we are going to be discussed in our next class. So up to this much we have to be stop our discussion today. You go through this video. If any doubt, you can contact with me. So thank you so much for watching this video. Thank you.